Okay, so let's take a look at what we've done today. We have essentially gone over the last part of 2.2 part 1 together. So we talked through the important ideas together, and we also went through some examples together today on the check for understanding for 2.2 part 1, exploring the density curves. So this is typically a little tricky, so you want to make sure you are understanding what's happening today. So important ideas. What we talked about yesterday was density curves. So density curves are basically a picture. It's a graph of data. And we can tell based on the picture, the shape of the picture, the graph, where certain things are located. And there's various shapes. So yesterday, some of our shapes were uniform, like a rectangle. Other shapes were like a symmetric or skewed. And then the biggest thing we want to remember is that in statistics, when we're looking at any sort of graph or picture of our data, the area under this curve or picture, as it were, this graph is always 1 or 100%, because it accounts for 100% of our data. So that's kind of the properties of a density curve. Then what we looked at is special locations, sort of. So we looked at different skews and like where the mean, the median would be with respect to the skews, or with respect to the symmetrical picture. So just knowing which one's bigger than the other. So just always thinking your mean gets pulled down towards the skewed parts. During this recording, if you're watching it to catch up, feel free to pause at any point so you can write these things down. And things, but I'm going to keep talking. So, okay, the other important ideas we had were the normal curve. So in statistics, the special density curve that we always use, because a lot of data follows this pattern, this bell curve pattern, is a normal distribution or a normal density curve. So this is basically always the shape, a bell shape, and somebody back in the day figured out if we put the mean in the middle, which for symmetric distributions makes sense, and we mark out some of these special spots, so 1 standard deviation up, 2 up or 3 up, and then 1 back, 2 back, and 3 back from the mean. There's sections of this curve or this graph have a certain area, and it all adds up to 1 or 100%. So I'm thinking of this in terms of percentages, and I'm just realizing that these look like 2s. This should be a 3. So 2.35. I'm awkwardly doing this with my mouse. Okay, so this is, there we go. So this is basically our normal curve with the various areas represented with our special spots. So basically between the mean and 1 standard deviation up, this section of the curve has an area of 34% or 0.34. So like 34% of your data is here in this spot, or 34% of it's here, or between these two spots, it's 13.5. So basically think of areas as your percentages. That's the biggest thing. So then we looked at first example together on the check for understanding. So basically we discussed that we have the data was a straight line. So it's like a uniform distribution. So I basically closed this off so it looks like a rectangle, because a rectangle is a shape that I know. I realized that the bottom of my rectangle has a length of 4 seconds from 1 to 5. That range is 4. And then it asks us, this is a density curve. So it's like, it's a rectangular graph, but in stats, we call it a density curve because it's basically representing our data in the form of a picture, and then the area underneath is always 1. So we asked ourselves, all right, if the length of the box is 4, the rectangle, how tall would the box have to be in order to have an area of 1 underneath, or 100% of the data essentially is underneath this picture or in this picture. And we said, well, if we take 4 times 1/4 or 0.25, that's going to give us 1. So then the height of my box has to be 1 or 1/4 or 0.25. Then using that information, we wanted to find a certain section of this box or this density curve. So using our density curve, it says about what % of the time will the light flash more than 3.75 seconds. So I marked out where 3.75 was. and it says more than, so I shaded up this way so I could see like, okay, this is the area or the section of my density curve that I want to know. So I redrew it down here. Basically, I'm at 3.75 and I'm going all the way up. And we determined in part A, or the first part, that the height of the box is 1/4. So to find the area of a rectangle, it's just length times width. So if I know how tall or what the length is here is 1/4, I just need to figure out how wide it is here. So 3.75 to 5 is a distance of 1.25, and multiplying those to get the area is 0.3125 or 31.25%. So that's telling us that in this data, using this density curve and this pattern, 31.25% of the time, the height will flash more than 3.75 seconds. Now, this third question is working backwards. So it says, calculate and interpret the 38th percentile of this distribution. So I am basically finding a percentile, which is from a location all the way down, like from that spot, equal to that spot, and less than that spot. So I kind of marked out an area. And basically what we know, if we know there's a certain spot, and the percentile is 38% or 0.38. I'm going from this location on down, and the area inside my box is 0.38 or 38%. So I'm working backwards. So this time I know the area. I got to work backwards to figure out the side length. So we did a little algebra here. So I wrote it in decimal form and fraction form, however you want to think about it. Basically, we know the height is as 1/4, and we just got to find the side down here, how long that is, so we can know where we're at. So basically, we just want to divide away the 0.25 to get x, because we're going from here all the way down. So we've got basically, if we go up to 1.52, then we know basically from here down to the end of my data, it's going to be 38%. So that's going to be my 38th percentile. So at 1.52 seconds, 38% of the data is at or below 1.52. Now in stats, we don't use boxes a whole lot. We use the normal curve. So the normal curve has various percentages in here for our special spots. So what we want to do is realize the data is approximately normal. So I got kind of crazy and circled all that. And then we have our mean and we have our standard deviation. So I'm going to mark those out every time. Just get used to doing that because you're going to do it for the rest of chapter 2. So the mean goes in the middle, and then we add a standard deviation going up. So like a z-score of 1, because that's 1 standard deviation above the mean. So that would be 67. Add 2.5 again for a second standard deviation, and then a third one, and then subtract 2.5 and again to get those spots. So we use that information to find some stuff. So it says about what percent of young women have heights less than 69.5 inches. So I first marked out where 69.5 was, and in red, and I shaded, it says less than, so I shaded to the left. So basically I want to find this area, but this is not a nice rectangle that I can just do length times width for. So I need to look back at my important ideas and thank the statisticians that figured out the various areas, if it's normal, that these areas apply every time. So basically this section had an area of 13.5, the next one was 34, 34, 13.5, 2.35, and 1.5. Basically, I just got to add up the sections I want, the ones I had shaded, and that's going to be my area. So this is 97.5 for my area, which is, I can think of like a percentage, or in this case, it's technically a percentile because I'm here at 69.5 and I shaded less than. So that's also a percentile. So a height of 69.5 inches, 97.5% of people are at or below 69.5 inches in this distribution of young women age 18 to 24. Similarly, I can also use this to justify answers. So in this case, it says a young woman with a height of 62 inches, is she unusually short? So I don't know, I got to figure out where like she is and what percent of the data is above and below her. So that's what I can do with this curve. So if I take 62 and shade below that, I can find that area by adding up those sections. So 13.5, 2.35, and 0.15. So if I add those three up, that should be 16 or 16%. So what that tells me is that 16% of people are at or below 62 inches. So if I kind of think about it, that also means there's 84% of people taller than her, because this whole picture adds up to 100% or one, the area underneath. So yeah, she's like super unusual, but like she's not super tall either. We could probably say she's below the 25th percentile. You know, there's only 16% of people shorter than her in this distribution. So yeah, she's not very tall. She's kind of short. Now, in terms of like super unusually short, that would be somebody like down here, like, you know, in the real tiny area. We can say that she's pretty short. So unusually short would like real short would be like down here, but she's also not very tall. I am the 62 inches tall. So yeah, but anyway, so that's what we did today. We just went through these questions together. Doing the things. So tomorrow, the lesson you'll do on your own, which is similar to this normal curve. So getting used to the idea of distribution is normal. So we have data, it's classified as normal. That tells me it follows a certain pattern. So bell curve. Based on that curve, it has certain properties. So somebody figured out various areas of the curve, which is great. We use it all the time. And then we use that to solve our problems. So this is pretty much our thought process from today. So that's what we did. Hopefully that makes sense. If it doesn't, or you still have questions, please reach out and email. This is a section that kind of takes a lot of thinking, and people get a little confused with it. So please reach out if you need anything.